Hi, I'm Pritish Kamath, and this talk is based on joint work with Omar Montasser and Nati Srebro, and we are all from TTI-Chicago. So, to quickly summarize, this work is about understanding the power and limitations of linear and kernel methods for supervised learning. This has been a very classically motivated research direction, and in particular, we could ask whether linear or kernel methods are capable of learning everything that is back learnable. And indeed, this has been studied for quite a while now, and there is a rich body of literature. But in the modern context, we were interested to understand the relative power of kernel methods as compared to that of deep neural networks, because uh, it seems that deep neural networks seem to outperform kernel methods on many practical benchmarks. So, a tantalizing question here is, could it be that all we are missing with kernel methods is the choice of the right kernel? And there is some hope for this because of the paper on the neural tangent kernel, which shows that the training dynamics of infinitely wide neural networks is essentially the same as that of a kernel method, with the kernel being the neural tangent kernel. And in fact, people have experimented with the NTK corresponding to some convolutional architectures and have found that these outperform other kernel method benchmarks. So, while it's hard to conclusively answer this question in practice of comparing kernel methods to neural nets, we could at least ask this question in theory. And indeed, there have been some recent works which exhibit theoretical settings where neural networks are provably able to learn, but no kernel method can solve that learning task. Right. So, so in this paper, we introduce a broad formalism to reason about such results and more, and we also prove some new ones. Okay. But before we even get to limitations, we have to formally define the scope of a linear or a kernel method. So a linear method would go by first choosing an embedding that maps inputs to a d-dimensional space, and then using the training data to learn a linear function over that space. And, and the goal is to minimize the population loss of the predictor that we output. So very commonly, the learning rule that is used is the empirical risk minimization rule, or the ERM rule, where we just choose a predictor W hat, which minimizes the empirical loss. So we could define the linear learning complexity of a hypothesis class as the smallest sample complexity of an algorithm that works by first mapping inputs to some d-dimensional space, such that for any distribution over the inputs and any hypothesis of interest that is generating the labels, the population loss of an ERM rule, of an ERM predictor, is small in expectation. So here I'm not focusing on the computational cost of computing an ERM. So the emphasis of this talk is entirely on sample complexity. So this definition by itself is not well specified because there could be more than one choice in defining an ERM rule. And in fact, any ERM based learning algorithm can be disguised as an ERM based learning algorithm over linear functions using essentially sparse linear regression or classification. Right? So, to make this definition meaningful, it makes sense to say that any ERM rule should achieve low population loss. So, once you commit to an embedding, you should not have any say over what ERM rule is being used. Any ERM rule should achieve low population loss once you have fixed this embedding. Okay, and to make this definition more powerful, we could also allow for a randomized embedding or distribution over embeddings, and this makes sense because even in practice, people use randomized features or even randomized kernels, such as the neural tangent kernel, for example. Okay. Now, the notion of dimension complexity was introduced almost 2 decades ago, where for any hypothesis class, it's defined as the smallest dimension you need to embed your inputs. So small as d, such that you can embed your inputs into a d-dimensional space, such that all hypotheses are realizable over that space as linear functions. So this was originally defined only for binary classification. So you can see this pictorially. But you can go ahead and define this for with respect to any loss function. Okay, so using generalization bounds that follow from standard dimension-based arguments, it follows that there is a linear learning rule whose sample complexity is bounded in terms of the dimension complexity of the hypothesis class, right? Okay, so this is great. And uh, that's why a lot of literature since has focused on proving lower bounds for dimension complexity of various classes. So a notable example is the class of all parity functions, which has dimension complexity that is exponential in n, where the class is of parities over n bits. And this is in contrast to the VC dimension, which is only n, and that's why you can learn this class with sample complexity that is linear in n. Okay, and there have been many more results proving lower bounds on dimension complexity in the circuit complexity or communication complexity literature, and where it is studied for a completely different reason. So we won't be talking about those, but for learning, dimension complexity gives a sufficient condition for learning with a linear rule. So we could ask whether it is also necessary. Okay, so well, clearly not, because we can define this notion of probabilistic dimension complexity, which we do, uh, which is defined as we require a distribution over d-dimensional embeddings, such that for any distribution over inputs, every hypothesis is approximately representable as a linear function over that embedded space. Okay, so the main focus is on, instead of exactly representing hypotheses, we are approximately representing hypotheses. And by the same dimension-based generalization bounds, we get that there exists a linear learning rule whose sample complexity is upper bounded in terms of this probabilistic dimension complexity. Okay, so this is cool, but you may ask whether this notion is really any smaller than the exact dimension complexity that I defined before. And indeed, we show that there exists a very natural hypothesis class where the probabilistic dimension complexity is exponentially smaller than the exact dimension complexity. So this notion can indeed, in some cases, be significantly stronger. Okay, but note that we are still talking about sufficient conditions for learning with the linear rule. So in order to talk about necessary conditions, we define a distributional version of probabilistic dimension complexity, where we require this embedding to work to work only for a pre-specified distribution over the inputs. So every hypothesis is expressible up to low error over this pre-specified fixed distribution. Okay, and what it follows from the representer theorem that this distributional probabilistic dimension complexity is is a lower bound on the sample complexity of any linear learning method. Okay, so this is great, but also what's also common in practice is to have a norm constrained ERM rule. So instead of mapping inputs into a finite dimensional space, you could map them into some space. I mean, it need not even be finite dimensional, but you map them to points with bounded norm. So here, the mapping itself might be implicitly represented as using a kernel, and then the ERM is then performed only over a bounded norm ball of hypotheses of linear functions, right? So the notion of margin complexity was introduced in a very analogous to dimension complexity to capture the power of these norm-bounded learning rules. And uh, while this notion was originally defined for classification, again, you can define this for with respect to any loss. And we analogous to dimension complexity, we define a probabilistic notion of margin complexity, where we require that your hypothesis is approximated by linear functions with small bounded norm. Okay, so it's very analogous to dimension complexity, and similar to before, instead of so we get that there exists a learning rule, a kernel learning rule with sample complexity that is upper bounded in terms of this probabilistic margin complexity. And we get this from standard generalization bounds that follow from norm-based arguments instead of dimension-based arguments. And from the representative theorem again, we get that the distributional dimension complexity that I defined earlier is a lower bound on the sample complexity of any kernel learning method. Okay, so to summarize all the measures that I defined so far, there exists a linear learning rule whose sample complexity is upper bounded by the probabilistic dimension complexity. There exists a kernel learning rule whose sample complexity is upper bounded in terms of the probabilistic margin complexity. And finally, the distributional probabilistic dimension complexity is a lower bound on the sample complexity of any linear or kernel learning rule. Okay, so in order to understand limitations of linear and kernel methods, it's important to understand lower bounds on this distributional probabilistic dimension complexity. Okay, so, and that's what we do. So let's start with the case of regression. So for squared loss, we show that the distributional probabilistic dimension complexity of class is lower bounded in terms of the statistical query dimension. So this is a quantity that was originally defined in order to study statistical query algorithms, but here we are using it it's a very different setting. Okay, and using this result, we can actually reprove the kernel limitations that were proved in these prior works. And in fact, this theorem of ours helps us actually to address an open question in this paper of Yehudai and Shamir. So this is great, but this is all about classification. All these prior works were all about regression. So what about classification, which is one of the major successes of neural nets? So can we also understand limitations of kernel methods for classification tasks? So here what we show is that for binary classification, we consider this hypothesis class of one sparse predictors. And we show that this distributional probabilistic dimension complexity is at least linear in N. Okay, so this essentially means that if you want to simulate sparse linear classification as a pure linear or kernel method, you would need sample complexity that is linear in N. So this is in contrast to the VC dimension of this class, which is only logarithmic in N. So it means that linear or kernel methods require exponential in VC dimension many samples for learning this class. Okay. So, but note that this lower bound is only linear in the bit length representation of the inputs. So that's any algorithm would require computational cost that is linear in the bit length representation. So in that sense, this lower bound is not that strong. So we could ask, can we prove a lower bound that is super polynomial in the bit length representation of the hypotheses and the inputs for some natural hypothesis class? And it turns out actually that proving this would resolve some long-standing open questions in circuit complexity theory. So this does not seem to be an easy task. So an open problem here would be to prove lower bounds with respect to other classification losses such as hinge loss or logistic loss. So finally, to quickly summarize, we introduced in this work, we introduced probabilistic variants of dimensional and margin complexity, where these notions go for approximating rather than exactly representing hypotheses. And we showed that these notions can be significantly more powerful than the deterministic exact variants that are studied traditionally. And most importantly, some of these measures are not just sufficient for learning with linear or kernel methods, but also necessary. So with that, we feel that these measures are more suited for understanding limitations of linear and kernel methods, and we hope that our results shed some more light on trying to compare the power of kernel methods relative to that of deep neural nets. So there are many exciting open questions here which I didn't mention. So I'm looking forward to discussing them with you at COLT. So see you there.